The most noticeable thing about the scores for the test was just they were pretty spread out, you know. So I just want to go through all these questions and try to point out the things that that I think are especially important for the future. Okay, so exam 2. First question, there's a gas in a piston cylinder. And it starts out at P1 of 5 times 10 to the 5th pascals and volume 1 of 0.4 cubic meters. And the process takes it to a second pressure of 2.0 times 10 to the 6th pascals. And we know that the relationship between pressure and volume is pressure times volume to the 1.3 is equal to a constant. Nick? Okay, so there's only one parameter we need to find in the first one. We need to find that constant, and we can use that first state to do that. So we have 5 times 10 to the 5th times 0.4 to the 1.3. Maya, right? Is equal to the constant, and so the constant is equal to 151,931, something like that. Okay, so we have this relationship that says pressure times volume to the 1.3 is equal to 151,931. And so we can use this to find the volume in state 2. So in state 2, we have 2 times 10 to the 6 times v to the 1.3 is equal to 151,931. So v to the 1.3 is equal to, 1.51931 times 10 to the -1, I guess. And then take the 1.3 root of that. So multiply or take both sides to the 1 over 1.3 power, and you get that the volume is, so for part A, the volume is 0.1377 meters cubed. One thing about that is there was a wording on the wording in number 1 said that it expands. It doesn't expand. I just didn't see that when correct that when I changed the problem. So can't cause any problems. Sorry, let me know if you think that really threw you off, and I'll consider that. But anyways, it doesn't expand. The volume gets smaller. And then second, we want to calculate the work for the gas. And the work is equal to the pressure dV. And the thing that people did most often, the problem people had most often, was that they integrated this whole so people integrated this times this dV. And well, for one thing, I mean, I guess you could calculate that. The people who did it that way didn't calculate it correctly anyways, but what you need isn't to integrate this expression. What you need is to calculate P as a function of V and then integrate with respect to V. So whenever you're doing this integration, what you need is pressure as a function of volume, okay? And so if your relationship is that P times V, the 1/3 is equal to this constant, you need to multiply both sides by V to the negative 1/3, and you get P as a function of volume is equal to 151,931 V to the negative 1.3. So then the work is the integral from the first volume to the second one, so integrating from 0.4 to 0.1377 of 151,931 V to the minus 1.3 dV. And if you do that integration, you get negative 251. I get 341 joules. And that sign makes sense because the gas contracted, the volume got smaller, and so you know that work is being done on the gas. Okay, so this is going to keep coming up in future sections that we talk about. If you're trying to calculate work done by the gas as an integral of PdV, whatever expression you have, whatever relationship you have between P and V, you need to separate P as a function of V, integrate it. Okay, the second one, so we have a device that's cooled convectively by airflow. So we know that Q dot is equal to, and this does not, we don't know the sign of this yet. We're going to have to consider that when we choose our system. But we know that Q dot is equal to H times A times the change in temperature. So temperature of the device minus the temperature of the air. And that's equal to 80 in SI units. That's the H. The A is 1 times 10 to the minus 2. And the change in temperature, we're given that the air is 20 degrees Celsius. Trying to calculate the temperature of the device. So that's in Celsius. And it's okay to leave that in Celsius for this case because that's a difference in temperature. And the difference in Celsius is the same as the difference in Kelvin. And then let's see, it's steady state. So the first law says that dE dt is equal to Q dot minus W dot, and it's steady state, so this goes away. And there's electrical power coming in, and the device is doing work, so that's work going out. Okay, so we have to think about the sign of work. Is work positive for work coming into the system or work going out of the system? Out. Yep, so the work that the device is doing is positive. The electrical work coming in is negative. So we have negative 50 plus 12. And so W dot is negative 38. Now we have to think about the sign of Q dot. The device is being cooled, so energy is leaving the system through heat. So is Q dot positive or negative? Negative. So negative 0.8 if you multiply those two together times T device minus 20. And then we can put that into the first law. 0 is equal to negative 0.8 TD plus 16 minus negative 38 and if you solve for TD, you get TD is equal to 67.5 degrees Celsius. Any questions about any of the signs on that one? Number 3, so gas is contained in a closed tank. The closed tank means the integral of PdV is equal to 0 because the volume is constant. An electric resistor in the tank transfers energy to the gas at 1 kilowatt. Okay, so an electric resistor is it's doing electric work on the system. Is W, I guess let's see. So are W or W dot going to be, are they positive if work is done on the system or positive if work is done by the system? By the system, on the surroundings. So, so this says that work is done at this given rate on the system. So W dot, and it's W dot because it's given in kilowatts, is equal to negative 1 times 10 to the third in watts. And then there's heat transfer from the gas to the surroundings. So is Q dot positive or negative? Negative. So Q dot is equal to negative 0.01 T squared. And the first law of thermodynamics says dE dt equal to negative 0.01 T squared minus negative 1,000. So dE dt is equal to negative 0.01 T squared plus 1,000. And then we want to calculate the rate of change of internal energy. That's the first one. So that's what we have here. And then the second thing we want to calculate is the change in internal energy as a function of time. So to do that, we can use separation of variables. So dE is equal to all of this plus 1,000 dt. You can do that because you can arrange this equation so that anything with an E in it is on one side, that's nothing. And over here, anything that is a function of T is connected to the dt. Yep. Right. That's right. Okay, so now integrate both of these. And you get that the change in energy is equal to negative 0.003 repeating T cubed plus 1,000 T. Any questions about that one? Because, so if we were calculating so what we're doing here is, let me do it sort of carefully. So we're going from E1 to E2, or E1 to, whatever this, to E at time T. And over here, we're integrating from T equals 0 to T, and, make these like a dummy variable. And so here you get E minus E1 is equal to negative 0.003 repeating T cubed plus 1,000 T. And this is just another way of writing the change in E. So, I mean, the basic idea is the fact that we wrote this as delta E, you can think of that as the constant integration that you normally put over here. You would either have to put some kind of constant over there. What you would probably do is put E1 over there, say that at time equals 0. All we know is how much the energy increases from there. Or if you happen to be given the starting energy, then you could just add that on. But yeah, in order to do, to integrate over boundary conditions like that, you need to know the values at the bounds of integration. Any other questions about that one? And then the last one, this is the interpolation one. Okay, so we have a saturated water vapor. In a fixed tank. the volume is 0.5 meters cubed. And it has an initial pressure, so P1 is 0.35 bar. Okay, so you can figure out what the temperature is to start, because it says it's saturated to start. And then you add heat to the vapor until the pressure reaches 0.6. So P2 is 0.6 bar. And the temperature is 236 Celsius. And so what you can expect to happen is, if this is saturated and you're adding energy to the system, you're taking this vapor out of being a saturated vapor and making it superheated. And so for this second state, you don't really expect to be able to use the saturated, the table for a saturated vapor, although you could, you can check to see if that's the case. But so if you look like at a saturated vapor table and you look at this pressure and this temperature, that's not going to match up with anything. And so it's a superheated vapor, and you can use those to find it. But neither of those are nodes that are given in the superheated vapor table. So we're going to have to do interpolation. And we're going to have to do that 3-step interpolation for 2 independent variables, because neither of those is a node. And we want to find first the mass of the water vapor. Second, what's the internal energy at the first state? And it asks for the total internal energy, not the specific internal energy. So we're going to have to use the mass of the vapor to calculate U1. Then interpolate to find the final internal energy. And then last, we want to find Q. Given that there's no change in the system's potential or kinetic energy. And so what that says is delta E is equal to Q minus W. It's a fixed tank. There's no work being done. So that's 0. And delta E, since there's no change in kinetic or potential energy, is just delta U. So you can rewrite this as U2 minus U1 is equal to Q. So once we calculate U2 and U1, then we can use those to calculate Q. So first for the mass, so it starts out as a saturated vapor. This is at state 1. And so you can use a saturated vapor table at, what did it give us? The pressure, right? At a pressure of 0.35 pascals, bar, right? And if you do that, you get that the specific volume is 2473.0 kilojoules per kilogram. So first we want to find the mass. for part A. Oh, oh, I see what, yes, thank you. I wrote down the wrong thing. Exactly. Okay, so V1 is 4.526 cubic meters per kilogram. And if you recognize that that is 1 over the density, you know, you can, or I guess maybe another way to write this is that the total volume, which is given, is equal to the mass times the specific volume. So this is equal to, let's see, V. So 0.5 is equal to the mass times 4.526. And so the mass is 0.1105, something like that, kilograms. Okay, so if you know those total properties and you know those specific properties, you can use those, the relationship between those two, to calculate the mass. That's true of specific internal energy, specific volume. The initial internal energy. Okay, so that in that same table, you can look up that the specific internal energy is 2473.0 kilojoules per kilogram. And so the total internal energy at that state is the mass times this specific internal energy. And you get 273.19 kilojoules. And then the long step is part C. That's the one where we have to interpolate. Now in state 2, if you look at the superheated vapor table, you get that the specific internal energy at a pressure of 0.35 and a temperature of 240 is 2720.3. This is in kilojoules. All of these are kilojoules per kilogram. U at a pressure of 0.7 bar and a temperature of 240 is 2719.3. At a pressure of 0.35 bar and a temperature of 200, it's 2660.4. And at a pressure of 0.7 bar and a temperature of 200, it's 2659.1. And last class or two, we've been talking about these approximations of different materials, incompressible liquids, ideal gases. And in all of the cases that we talked about, we approximate the specific internal energy as a function only of temperature. And so what you expect that to mean is that there isn't too much change in the specific internal energy as you change the pressure. And there's relatively a big change as you change the temperature. And you can see that there. In both of these cases, as the pressure changes, you get a very small change in the internal energy, there to there. But as the temperature changes, that's where the big jump happens. So you get a fairly good approximation even if you skip the, I didn't want you to do that, but just intuitively, the difference isn't that big if you skip the step of interpolating over the pressure. And so you can interpolate in either order of steps. You can first do the interpolation over the pressure, first do the interpolation over the temperature. So I guess what I did was, for step 1, specific internal energy at 0.6 240. Then I did the specific internal energy at 0.6 bar 200. And then I interpolated those two using those two to get specific internal energy at 0.6 bar 236 degrees. And I got a value of 2713.57 kilojoules per kilogram. Now you just have to remember what you're being asked in the problem. That's the big part of doing this problem. But we're looking for, so this is our little u2. We're looking for big u2, so it's going to be the mass, 0.1105 times little u, 2713.57. And you get a value of 299.77 kilojoules. And now go up to this relationship is what we're going to use. We know U2, we know U1, we can calculate Q. So 299.77 minus 273.19 is equal to Q, and that's 26.58 kilojoules. A few people went all the way through the hard stuff and then just forgot to sort of finish it out. They did calculate the total internal energy, but then didn't put it into the first law. I hardly took off anything for that, but that happened a few times. Anybody have any questions about that? Yes. Yep. Nope. Okay, so did you do your first 2 interpolations to get to a pressure of 0.6 bar or to get to a temperature of 236? Oh yeah. Yeah. Mm-hmm. Yeah. Nope, it doesn't matter. That's right. Yep. You won't get the exact same thing if you interpolate in the opposite order, but there's no reason to believe one of those 2 interpolations over the other one. I could have done my first step I could have done an interpolation for U at a pressure of 0.7 bar and a temperature of 236. And then this one at a pressure of 0.35 bar and a temperature of 236. And then interpolated to get the pressure of 0.6 seconds. And it wouldn't give that exact same thing, but it would be just as good an approximation. It would be close, hopefully. If it's not close, then you're interpolating things that are probably too far apart. Any other questions about that one? Yeah. No. Was that not on there? Okay. No, you should not. Okay. Sorry about that. If that happens, let me know and I'll write it on the board. And if anyone thinks I missed, you wrote something and I didn't see it, or you want to argue for a couple points here or there, whatever, come talk to me in the next week, please. Just don't wait a ton of time, but sometime pretty soon, and I'd be happy to talk about it. Or if you want to make an argument for why you got derailed by either me not giving you the formula for convection or the thing that said expanding, I'm happy to listen to arguments, but let's just do it fairly soon. Okay, that's the test. The last time we talked about simplified material models for liquids, the main one being incompressible materials. That can also be used for solids, but we won't do any solids. And second, for vapors, for gases, and that was the ideal gas law. And now we're going to talk about a simplification of a process. So those are both relationships between properties in states. So now one process simplification. And that is the assumption of a polytropic process. And we've already used this simplification or used this equation before, but it's the assumption that the pressure times the volume to some power is equal to a constant. And R is usually near 1. Like between about 0.7 and 1.3, something like that. To use this, you need to know what that exponent R is. So how do you know that? Normally you would know that from experiments on this specific process. You're taking measurements relating the pressure and the volume and then finding that they approximate that. One thing to notice about this is that if R is equal to 1, then you're assuming that this is an ideal gas a constant temperature. Because, you know, the ideal gas law says PV to the first is equal to nRT. And if you're keeping the same number of molecules in there, same mass of material, keep the temperature constant, this side would be a constant. Okay, so we can come up with a formula that gives you the relationship between pressure and volume. Okay, here's what we're doing. We can express a formula for the work of a general polytropic process. And so let's go through that. And you don't have to memorize this derivation. It's not very long. If you remember anything about it, I just want you to kind of vaguely understand what the starting point was and the ending point. But I'll give you this formula if you need it on tests or homework or whatever. Okay, so work is equal to the integral from V1 to V2 of PDV. We know that PV to the R is equal to some constant C. So P is a function of volume is equal to C times V to the negative R. And so the work is equal to the integral from volume 1 to volume 2 of C V to the negative R dV. And what do you get if you integrate, you know, that C is a constant, so you can pull that out of the integral. But what do you get if you integrate V to the negative R dV? So C V negative R plus 1, I'll write that as 1 minus R, divided by 1 minus R, evaluated from the volume at state 1 to the volume at state 2. And notice that that is equal to C. So C times V to the negative R is the pressure, right? And so C times V to the negative R plus 1 is pressure times volume. So I can get rid of that C. We have pressure times volume over 1 minus R, evaluated from V1 to V2. And so now evaluate this at the limits. You get, so the pressure, so evaluate this at volume 2. You have to evaluate the pressure at volume 2 also. So this is the pressure at state 2 times the volume at state 2 over this, minus the pressure at state 1 times the volume at state 1 over this. And so the final formula is P2 V2 minus P1 V1 all over 1 minus R. Okay, so this is for a general polytropic process. That means if you know the beginning and ending pressure and volume for any polytropic process, you can calculate the work of expansion. You can calculate W. Okay, so that's a helpful thing. That's not true of like a gas in general. If, besides being a polytropic process, you can assume that you're dealing with an ideal gas, then you can calculate the work with even less information coming in. That sort of makes sense because an ideal gas gives you relationships between variables at each individual state. So if the polytropic process represents an ideal gas, you need even less information to calculate W. So let's say that N is the number of moles. We know that for a general polytropic process, the integral from volume 1 to volume 2 of P dV, this is what we just calculated, is equal to P2 V2 minus P1 V1 over 1 minus R. The ideal gas law says that PV at any state is equal to N times the molar universal gas constant, R, times the temperature, so let's substitute the ideal gas law into, so let's call the ideal gas law 2 star, double star, call this one star. So substitute 2 star into star, and you get that W is equal to, we're just going to replace these two terms using the ideal gas law. And you get N, the number of moles, times the universal gas constant, divided by the quantity 1 minus R, times the quantity T2 minus T1. So what that tells us is if we have both a polytropic process and an ideal gas, then we can calculate W from the temperature T1 and the temperature T2 alone. Yes. Oh yeah, you can't use any of that. So okay, finish your question, sorry. Okay. So normally in a process, you don't have a constant temperature. Like imagine, so if you have an ideal gas in a piston cylinder system and you compress it, you know, the ideal gas law applies. It might be a polytropic process, but compressing the ideal gas is going to increase the temperature. If you know that it's if you do happen to have the case where the temperature is constant and it's an ideal gas, then yeah, you can't use this approach. Just like you said, you're dividing by 0, and you can't do it that way. But you could go through a similar approach. Like, look at what would happen up here if R was equal to. So if you had that PV to the first was equal to C, so that's the case of an ideal gas with a constant temperature, then pressure as a function of volume would be equal to CV to the minus 1. And when you did your integration, you just have to use natural log and come up with a different formula for it. So yes, you make an important point. So notice these formulas don't work for R equals 1. That'd be a good question, actually, to do that derivation for R equals 1. Any other questions about that? Okay, so let's just do an example. Obviously, if we're just using the formulas, doing these calculations is pretty simple. But so here's the type of thing you could use this for. So let's say we have 0.5 moles of an ideal gas. And it starts at a temperature of 120 degrees Celsius. And it's compressed in a polytropic process. And experimentally, we figure out that P times volume to the 1.2 is equal to a constant. And we want to know what's W. Okay, so first of all, what do we expect the sign of W to be? Gas expands, W is positive. This gas is compressing, so we expect it to be negative. Work is equal to N times the universal gas constant over 1 minus R times, oh, we don't know the final temperature. Oh, yes, we do. It's compressed in a polytropic process until T2 is 200 degrees Celsius. So W is this times T2 minus T1. And so W is equal to 0.5. I'll do all this in SI units, times 8.314 divided by, this is where the negative comes in, 1 minus 1.2 is negative 0.2 times the quantity 200 minus 120. And I can use degrees Celsius for that because it's a difference in temperatures. And I believe what you get here is negative 1,662.8 joules. What? Because I gave that in this problem, I gave that R was equal to 1.2. Okay, so that's what, so whenever you see PV to some power is equal to a constant, that's a polytropic process, and the R is the exponent on the volume. Yes. If there's no heat exchanged, then yes, that's right. I can't remember. Let's see. So if there's I mean, I guess that, yeah, I guess that must be true. Just by the 1 minus R has to be positive then in that, well, but the temperatures go in reverse. No, I don't think that relationship is true because then you'd have a ending temperature that was lower than a starting temperature, so that would give you that would switch the signs on its own for the temperature part. Right. That's right. That's right. So if you switch from compression to expansion, you have to switch the sign of work. So yeah, I don't think it's that simple a relationship on the exponent, and I don't really have any know of any like rules for what to expect that exponent to be. I just think of it as an experimental value. Any other questions? Okay. All right, so the next thing we're going to talk about, so far, when we've used the first law of thermodynamics, our system has been a fixed amount of material. You know, it's been like a gas contained in a cylinder, and it can compress and expand, but we're always talking about the same number, the same units of material, you know, the same gas molecules. But now we're going to think about this stuff in terms of control volumes. Okay, so for some types of processes, it's easier to analyze a fixed volume where material moves in and out, you know, material being the gas or the liquid. Than a fixed chunk of material. And so when the examples, so we'll use this for compressors, pumps, valves, nozzles, cases where the movement of a material through the device is fundamental to how that device works. In those cases, we'll use a control volume approach. And in control volumes, there are going to be two balance laws that we're going to use. For now, because we'll come back to control volumes when we go to the second law of thermodynamics. But for now, there are two balance laws. The first one is conservation of mass. And the second one is conservation of energy, which is the first law for control volumes. We don't have to specify conservation of mass for control volumes because when you're analyzing a fixed amount of material, conservation of mass doesn't give you anything. But it will be a useful tool here. Okay, so the first one we're going to talk about is the mass rate balance. That's conservation of mass. And what it says is the rate of change of the mass that's contained in the control volume is equal to the rate at which mass comes into the control volume minus the rate at which mass leaves the control volume. Okay, so the MCV dt is the rate of change of mass in the control volume Mi is the rate at which mass enters the control volume through all of the inlets. So the subscript I is for inlet. And ME dot is the rate at which mass leaves the control volume through the exits. Okay, so it's a pretty obvious statement, but it's going to be useful in this equation form. It just says that if you have more material coming in through the inlets than you have leaving through the exits, material is building up inside your control volume. If the exit more is leaving than coming in, the net material is leaving. If you're in steady state, all properties have to be constant. And so that just says that there can't be any change in mass in the control volume. And so the mass coming in the inlet has to be equal to the mass leaving through the exits. Okay, so to calculate Mdot, so this is the rate at which material is coming in or going out. We're going to use just an algebraic formula. Mdot is equal to, so first think of it as it's, bless you. So the mass leaving is the volume flow rate, how much volume is going through, times the density. That makes sense. And I'm going to write it like this. It's the density times the area of the opening, the area of the inlet or the exit, times V, and be careful, this V is, okay, so this A is the area of the opening, and this V isn't the volume. That is the average velocity of the flow. So be really careful with that. There are going to be times that you're going to see that and it's going to mean volume, and other times where it's going to mean velocity. Be sure you know what context that makes sense in. And since we don't deal in density that often, the way of writing this that's going to be more useful is A times velocity divided by the specific volume. Any questions about that? Okay, let's do an example. What? This is, the big V is still velocity. I just, 1 over the density is the specific volume, so that's all I did here. Actually, let's do this example next time. Let me say something else to just set up for this example. This isn't something we're going to do in problems, but I think understanding, wrapping your head around simple differential equations is going to be a useful thing in your future mechanics classes. The most common kind of differential equation that you'll ever have to solve in classes is ones that you can use separation of variables for, separable differential equations. And all the ones we've talked about so far are of that type. But another one doesn't come up quite as often, but it's a useful thing to have in mind, is first order linear ordinary differential equations. The ordinary means there's only one independent variable. So in mechanics and dynamics and stuff, usually the independent variable is time. Although sometimes it can be a spatial independent variable. First order means the highest derivative is a first derivative. And linear means that, so every differential equation, you're trying to solve for a function of the independent variable. You're trying to solve for y of t or f of t or something. The linear means that you never have those dependent variables, those functions multiplied together. You never have, so if you're solving for the function y of t, you never have a y squared, or you never have a y times a y prime, y dot. And so you can write this in this form. Any first order linear differential equation, you can write in a form like this. Y dot, so time derivative of the time derivative of y plus p, some function p is a function of time, times y is equal to some function q of t. No, that is if you're dealing with systems. If I'm thinking of the thing you're talking about, if you're dealing with a system of differential equations, then you use the eigenvalue thing. There's an easy approach to this, and it's based on turning the left side into a total group. It's basically based on the product rule, and you don't have to know the derivation to, like, the main thing that you should be able, well, that eventually you want to get comfortable recognizing is just seeing an equation like that and recognizing that it's in that form, because ordinary differential equations in general are hard to solve. If you happen to see one like this, you can solve it in a closed form, and that's a really useful thing. Well, I'm going to, okay, I'll tell you how to do that at the start of next time. We'll go through an example that uses it, and then we'll go on to the first law.